is one of humanity's most ancient chemical reactions, and one of the most useful ones. Whether it's for working metal or keeping warm, cooking or powering an engine, one of the most important things is the fuel-air mixture. The art and the science is to get the right proportions of oxygen to fuel to get the most heat and least pollution. This heat is coming mainly from the chemical reaction between carbon and oxygen. The amounts of each one, known as proportions, will control how much heat is given off. Proportions are also critical in rocket fuel. Rockets have to carry both fuel and oxygen and cannot afford to carry fuel which they can't burn. To measure these proportions, we use a chemical measure called the mole. We're going to test a series of rocket launches using various proportions of hydrogen and oxygen. This plastic bottle is the rocket, and we are bubbling hydrogen into it. To bring in oxygen, we let the water run out. Air comes in, bringing oxygen with it. We need to find out whether it would go further with a different proportion of hydrogen to oxygen. We know from this equation that we need 2 hydrogens to 1 oxygen to make water. But how do we measure this? By mass? By volume? Or by using another measure? Let's try measuring the reactants by volume. In this case, we're putting in 1 liter of hydrogen from a balloon. Now, let's change the tubes and put in half a liter of oxygen. So, they're in the ratio of 2 to 1 by volume. In this bottle, the gases are in proportion by mass. The hydrogen is very light, and 1/10 of a gram takes up around 1 liter. Whereas half this mass of oxygen only takes up this space. It is much heavier. The blue markers show proportions of the gases in these plastic test bottles. We are going to ignite each gas mixture and see how proportions affect the size of the explosion. We're digging them into the sand after making sure there's no rocks that could be blasted and cause injury. We'll ignite the mixture from a safe distance. First, we will try to ignite this bottle where the proportions are 2 to 1 by mass. 3, 2, 1. There's a spark but no ignition. Now let's try the other extreme, which is mostly oxygen. Now, where it's mostly hydrogen, is there enough oxygen to ignite it this time? This leaves the one where the proportions are measured by volume. 2 volumes of hydrogen to 1 volume of oxygen. Here we have demonstrated the importance of getting the proportions right, and with gases, the importance of measuring by volume. So, using the results of our field trials, we go back to our rocket for another launch. Measuring this time by volume, we take 2 volumes of hydrogen and enough air to give us 1 volume of oxygen. The other 4 parts are nitrogen.
All the second stage tanks now pressurized. 35 seconds and counting. We are still go with Apollo 11. Ignition sequence start. 6, 5.
So, with gases, volume does seem to be the way to go. Does the same rule apply to more complex fuels, such as propane? Here we're going to mix equal proportions of propane and oxygen in a soap bubble. We will then light it. If there is complete combustion, this gives a blue flame with a bang. Incomplete combustion will give a yellow, sooty flame. Incomplete combustion. Once we balance the equation, we can see that 1 molecule of propane needs 5 molecules of oxygen to burn completely. So let's try 1 volume of propane to 5 volumes of oxygen. Yes, that's a good reaction. Now let's compare propane and hydrogen as fuels. Would you expect propane to release more energy than hydrogen? You can get a clue from the amount of oxygen it requires to burn. This is hydrogen and oxygen in a bin filled with water. There are 2 parts hydrogen to 1 part oxygen. Now, propane and oxygen, 1 to 5, measured by volume. You don't hear much about gas explosions, but many accidents are caused when gases ignite. In the correct proportions, they are deadlier than dynamite. So for this reason, storing gas cylinders inside the house is asking for trouble. They are best stored outside where they are cool and ventilated. So we have learned that proportions of gases are measured by volume. But what do we do when we measure out a solid like carbon reacting with a gas like oxygen? If we used equal volumes, they would be totally out of proportion. For instance, when we combine the oxygen in this bottle with a burning candle, the flame goes out when most of the oxygen is used up. But only a small amount of wax has been burnt. It's the same at the blacksmith's forge. A fan or bellows feeds a large quantity of air to the fire. In this fire, carbon is combining with oxygen. If we want to predict how much carbon and oxygen will be needed, then we can count the atoms. One atom of carbon needs one molecule of oxygen to produce one molecule of carbon dioxide. As an example, a bolt plus 2 nuts gives this bolt-nut combination. They combine in fixed ratios, just like atoms and molecules. So 100 bolts will need 200 nuts. We could count them, but if we knew the mass of one nut, it's easier to weigh out 200. However, even with the same thread, there are nuts and bolts of different masses. So, we'll have to change our calculation accordingly. And it's the same with atoms. Each atom has its own atomic mass. Like the nuts and bolts, we can combine elements on the left with those on the right. 1 gram of hydrogen will combine with 19 grams of fluorine, or 35.5 grams of chlorine, or 80 grams of bromine. Instead of a gram of hydrogen, we could use 23 grams of sodium, or this could be interchanged with 39 grams of potassium. These quantities we have been using are quite convenient in the lab. They are the atomic mass expressed in grams. We call this measure the mole. Each of these dishes contains 1 mole. The mole represents a definite number of atoms or molecules for a solid, liquid, or gas. This balloon contains 1 mole of any gas you'd like to name. It is 36 centimeters in diameter and contains about 24 liters. A mole of any gas has about this volume. This is why we were able to measure the hydrogen and oxygen by volumes in our rocket fuel experiments earlier on. Each mole has the same number of atoms. The atoms are very small, and a mole has 602,000 million, or 6.02 times 10 to the 23rd. This is called Avogadro's number. It's such a huge number that if we had Avogadro's number of eggs, we could cover the Earth to a depth of 100 kilometers. And there are many units of measurement. The mole is just one of them. A mole is a measure of number, not mass. That's why we've chosen the mole to measure chemicals. The mole of any substance is the atomic mass expressed in grams. But we have to realize that sometimes it's more convenient to work with atoms, and at other times with molecules. We must remember which one we are working with and not get mixed up. The easiest way to work out the number of moles in a sample is the number of moles equals mass in grams of the sample. divided by the average atomic mass, which can be found in the periodic table. Example 1. If a mole of sulfur molecules has a mass of 256 grams, how many moles of sulfur atoms are present? We divide the 256 by the atomic mass, which is 32. This gives us 8 moles of sulfur atoms. Example 2. How many oxygen atoms are in 36 grams of water? If a mole of water has a mass of 18 grams, 2 moles of water is 36 grams. So there must be 2 moles of oxygen atoms. This amounts to 2 times Avogadro's number. Example 3. If there are 144 grams of magnesium being burnt in these fireworks to produce white light, what mass of magnesium oxide will be produced at the end of the display? The atomic mass of magnesium is 24, and the atomic mass of oxygen is 16. 2 moles of magnesium atoms combine with 1 mole of oxygen molecules to give 2 moles of magnesium oxide. To find the mass of magnesium oxide, step 1 is to convert masses to moles. If we divide the mass of magnesium by the mass of 1 mole, we get the number of moles. Step 2. Use the equation. 2 moles of magnesium produce 2 moles of magnesium oxide. 6 moles of magnesium will produce 6 moles of magnesium oxide. Step 3. Convert moles back to masses. Find the mass of 1 mole of magnesium oxide. Then it's easy to work out the mass of 6 moles of magnesium oxide produced by the fireworks. So the answer is 144 grams of magnesium produces 240 grams of magnesium oxide. Great! Now we fully understand the concept of the mole.